Assalamu alaikum everyone. Welcome to the International Conference of Marine Technology. The paper I'm going to present today is titled Influence of Different Contrarotating Propeller Boss Cap Fins on the Hydrodynamic Performance of Marine Propellers with Propeller-Rudder Interaction. My fellow authors are Professor Dr. M. Shahjat Atarafdar and M. Abdul Qadir. We are from the Department of Naval Architecture and Marine Engineering, Kuwait, Bangladesh. I am Taib Ahsan, a recently graduated naval architect from Kuwait, and I will be giving the presentation today. Firstly, I would like to inform you all about the table of contents of our presentation, an introductory part consisting of the objective and the literature review, a methodology part, then we have the results that we are going to discuss, and then based on that, the conclusions that we have drawn and some future recommendations. The objectives of our paper are to analyze the turbulent flow around the conventional propeller VP1304 with and without contrarotating propeller boss cap fins by using K-Epsilon turbulence model with Wimpelform algorithm, to assess the numerical uncertainties and modeling errors for the CFD simulation, to graphically compare the open water characteristics of the conventional propeller VP1304 with and without different contrarotating propeller boss cap fins for a range of advanced coefficients, to study the effect of propeller-rudder interaction for using Crpbcf, to study the effect of contrarotating propeller boss cap fin on the rudder drag coefficient and lift by drag ratio. As you can see here, we have done an extensive amount of literature review on the topics of various propulsion systems, energy-saving devices, and how they improve the propulsive efficiency of a ship, dating back from 1955 to recent years. However, we will try to summarize the key papers in this presentation. We all know that increase in propulsive efficiency not only favors ship owners by saving fuel costs, but also benefits the environment by decreasing carbon emissions. Nevertheless, environmental regulations are becoming more demanding, such as this regulation that aims to reduce greenhouse gas emission to at least 55% below 1990 levels by 2030. This is a significant increase compared to the previous target of 40%. One possible solution might be energy-saving devices. One of these energy-saving devices is the propeller boss cap fin. It was introduced by Augie et al. In 1987. Their model experiments showed 1 to 2% increase in propeller efficiency. Then various parametric studies have been done on them, and optimization studies like Mizzi et al. And Stefano Bergaro showed that gains from 1.3% up to 4% can be achieved for optimized PBCF. However, pivotal findings of Kimura et al. Showed that PBCF exhibits increased energy saving when combined with other energy saving devices. In 2016, Sun et al. Results indicate that the attachment of a PBCF increases the resistance of the rudder. However, later on in our presentation, you will see that the contrarotating propeller boss cap fin overcomes this problem and actually decreases the resistance of the rudder. Further back in 2014, Howe et al. Showed that the addition of a rudder results in an increment in propeller efficiency. This is still consistent with our findings. These results show that propeller-rudder interaction is a noteworthy topic to consider when investigating energy-saving devices such as PBCF. Another noteworthy energy-saving device is the contrarotating propeller. In 2009, Ghasemi found that CRP systems may raise the propeller efficiency around 2 to 3% from their conditions. In 2017, he et al. Proved that CRP surpasses the single propeller in both efficiency and stability. They observed an up to 2.2% increase in efficiency. In 2021, Wang et al. Results suggested that the vessel with a hybrid contrarotating propeller-podded propulsion showed a larger effective wake fraction, a smaller thrust deduction fraction, a higher hull efficiency, and a overall higher 4.12% higher propulsive efficiency compared with the single screw vessel. Later on in 2022, Zhu et al. Took the contrarotating propeller and the propeller boss cap fin and combined them to get a new novel energy-saving device called contrarotating propeller boss cap fin. However, they introduced this energy-saving device and its benefits and studied it at different revolutionary speeds. They left the frontier at that point for us to explore, and we further pushed this boundary to explore different types of contrarotating boss cap fins and different parameters such as diameters and then we attach the rudder to see the contrarotating propeller-Boscap fin rudder interaction. We all know the fundamental equations of fluid flow are the Navier-Stokes equation. However, because we are considering turbulence, we are using the Reynolds average Navier-Stokes equation, where the turbulent viscosity is calculated by K-Epsilon turbulence model. As you can see here, the turbulent kinetic energy and turbulent kinetic dissipation rate, two additional equations are solved to find the turbulent viscosity. We use the pimple algorithm, which basically consists of one inner piezo loop and an outer pimple loop. To account for the dynamic meshing, we use the sliding mesh method, which is implemented by using arbitrary mesh interface in OpenFOAM. This is our meshing flowchart. We have used three different types of geometry here. Namely, the first one is the conventional propeller, which we use to validate. Then we attach the hub to it in order to make space for the contrarotating propeller-Boscap fin to fit and to create the realistic scenario of a hub vortex, and then the contrarotating propeller-Boscap fin and conventional propeller setup. These are the dimensions of the VP130 for propeller. This is a transverse section of our mesh, and the dimensions are given here. As you can see, in order to mimic the contrarotating propeller-Boscap fin rotations, we have to use two different rotating regions, each containing two patches, one still and the other one rotating at the prescribed rotating speed. These are called AMI patches. And this is our total mesh containing the contrarotating propeller-Boscap fin, the main propeller, and the rudder. These are our boundary conditions. These are pretty basic and standard boundary conditions in order to simulate the flow around the propeller. However, this cyclic AMI boundary condition, which enforces a cyclic condition between the pair of boundaries, is unique to OpenFOAM. However, we can see the velocity of advance here, the no-slip condition, and our inlet-outlet, and the valve functions here. Now we will be discussing the results of our paper. As you can see here, we have tabulated the numerical and experimental results and made a comparison. Although there is some error throughout the range of advance coefficients, the curves do agree well with each other. Nevertheless, there is some increased error in the higher advance coefficient range. As the advance coefficient increases, the resistance of the propeller increases as well. This results in a smaller value of thrust, which is more susceptible to error. Because we're doing a comparative analysis, we deem this level of accuracy acceptable. Here we have compared the propulsive efficiency of the conventional propeller and the conventional propeller with contrarotating propeller-Boscap fin of 0.25 diameter of the main propeller and of 0.325 diameter of the main propeller. For all these cases, the efficiency did increase, and this increase in efficiency seems to increase with the increase of advance coefficient. In this analysis, the difference in efficiency increase for the different diameters were on average 0.52% and a maximum of 0.87%. This increase is due to the mitigation of the hub vortex. As you can see on the left along the propeller axis, there is a loss in momentum here. However, for the contrarotating propeller-Boscap fin case, this loss is sort of gained back. And for the comparison of different diameters, as you can see, the larger diameter has a much more higher momentum here. The velocities here are greater compared to the smaller one. This results in a higher increase in efficiency for the higher diameter. After making comparison of the diameters, we have chosen to compare two different types of contrarotating propeller-Boscap fin. Here with the similar design, we chose the main propeller for the auxiliary propeller, and for a B-series propeller of the same pitch by diameter ratio or blade area ratio, all the dimensions are the same except for the blade sections themselves. As you can see, for both cases, the propulsive efficiency usually increases. However, the one similar to the main propeller design performed better. The difference between the increase in efficiency of the two cases grow larger as the advance coefficient increases. In this analysis, on average, the contrary propeller boss cap fin with the similar type of auxiliary propeller performs 0.86% better than the contrary propeller boss cap fin, which is of B series type. If we compare the two velocity profiles, we can see that the similar auxiliary propeller performed well in mitigating the hub vortex compared to the B series one. As you can see, there's a huge loss in momentum here, however there is none here. On this side, we have compared all three types of contrarotating propeller boss cap fins here. As we can see, on average, the contrarotating propeller boss cap fin with 0.25 diameter increased the efficiency of 1.07%. And moreover, the contrarotating propeller boss cap fin of 0.325 diameter increased the efficiency 2.05%. And the contrarotating propeller boss cap fin with 0.325 diameter B series propeller increased it only 0.65%. On an average, all these cases result in an average increase of 1.26%. We now move on to the part where we add a rudder behind the propeller. As you can see, the base case conventional one is here on purple. If we add the rudder behind it, it jumps up to this yellow point. On an average, the conventional propeller gained 1.28% more efficiency. On top of that, when we add the contrary propeller boss cap fin, which is the blue line here, when we add the rudder behind it, actually jumps up to this green line here. On top of that, the contrary propeller boss cap fin rudder system gained an average of 2.04% and a maximum of 3.41% efficiency compared to the conventional propeller rudder system. A similar trend can be seen when the rudder angle is 15 degrees. The previous one was on 0 degrees, this one is 15 degrees, although the efficiencies vary in the level of increase. However, they do show the similar trend of increasing. We then took the rudder drag into consideration. As we can see that the propeller rudder system, conventional one, is the blue line here, and the yellow line represents the contrarotating propeller boss cap fin propeller rudder system. To add the range of advance coefficient, the rudder drag coefficient C rudder at 0 degrees of the contrarotating propeller boss cap fin system is significantly less than the conventional propeller rudder system. On average, 17.96% and maximum 35.89%. Later on, we analyzed the lift by drag ratio. As we can see, the contrarotating propeller boss cap fin rudder is significantly higher in terms of lift by drag ratio throughout the range of advance coefficients, on an average 5.69% and a maximum 7.27%. This increase in lift by drag ratio may result in greater maneuverability for a ship. Moving on to the velocity profiles, as we can see, the contrarotating propeller boss cap fin accelerates the fluid around the rudder, which results in a lower pressure and then hence lower pressure drag. And when it has an angle of attack, the fluid on top of the foil has an increased velocity compared to the conventional one, which results in a higher lift. We now move on to our grid conversion study. As you can see here, we started from 0.84 million, then we systematically refined it to 1.36 and then to 2.69 million. At every refinement level, the percentage of error for open water efficiency decreased significantly. And as you can see from the time of simulation, that each simulation takes quite a long time. Then if we represent them graphically, we see a monotonic convergence. We have done the verification study for advance coefficient 0.8 according to the paper of Stein et al., where they used the Richarlison extrapolation to calculate the uncertainties. The corrected value of the propulsive efficiency creates an error of 3.428 with the experimental data. And these are the conclusions that can be drawn from the results. Good agreement between EFD and CFD data for VP130 for propellers, open water characteristics, except for high advanced coefficients. The contrarotating propeller Boscap fin was able to increase the open water efficiency around 1.26% for the cases in this study. For the investigated dataset, an increase in the diameter of the contrarotating propeller Boscap fin leads to an increase in propeller open water efficiency. For the investigated types of contrarotating propeller Boscap fin, the one similar to the main propeller performs better compared to the different type. Moreover, the contrarotating propeller Boscap fin Propeller-Rudder system exhibits significantly larger values of propeller efficiency compared to the conventional Propeller-Rudder system. These gains in efficiency are observed at both neutral and 15 degrees of angle of attack. The contrarotating propeller Boscap fin reduces the resistance of the rudder substantially. It also increases the lift by drag ratio of the rudder. The effect of contrarotating propeller Boscap fins or propeller-rudder system is far more prominent than its effect on the propeller by itself. And these are the recommendations for future work. Structural analysis and feasibility studies of the propulsion system are required to determine its successful integration into the marine industry. Parametric and optimization-based numerical studies of higher fidelity that overcome or minimize the numerical errors. Experimental studies in cavitation tunnels or towing tanks can further our understanding of the contrarotating propeller Boscap fin with greater accuracy. Self-propulsion simulations of the contrarotating propeller Boscap fin behind the hull can describe its propeller-hull interaction. 6-degree of freedom maneuvering simulations can determine its applicability to various types of ships. The contrarotating propeller Boscap fin's behavior in conjunction with other ESDs. Thank you. These are our references. You can find some of these case directories in my GitHub.